Mathematics made easy, no more fear. Target online class, we got you. Wherever you want to from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Toydel online group, online school, or online class. So today we want to look at subgroups. So before we go into the topic, I would like to do a recap of what we have done in the past. So you can check my videos on binary operations, mapping, groups, an example of groups, for you to have proper understanding about this concept. So we want to talk about subgroups today. So let me start with binary operations. There are 6 properties. There are 6 properties that we discuss under binary operations. The first one is when it's closure property. We talk about closure property under binary operation. We talk about closure property. We talk about associativity. We talk about commutative property. We talk about distributive, existence of identity element, and existence of inverse element. So all these 6 properties will actually come into play when we want to talk about the four out of the 6 properties is what we consider when we introduce group. So for a set, say it's set G under a binary operation asterisk to be a group, there are 4 properties that must be satisfied. The first one is a closure property. That is, if you pick any element in G, the element must be closed in G under this binary operation. The second property that we check is associative property. That is when you pick 3 elements, irrespective of the arrangement, you must be able to satisfy this G. This element, this set G must satisfy associative property. Then we also look at existence of identity elements. Then the last thing that we check for this G, asterisk to be a group is when we talk about inverse elements. So I want you to check, you can check my videos on groups to have proper understanding. So let me introduce subgroups properly. So a subgroup, as we have it on the board, a subgroup of a group G is a subset H of G. A subgroup is a subset of a group H of G, which is a group under the binary operation which it inherits from G. That is, if G, this is a set, G is a set, and there is this binary operation asterisk beside G. If G, asterisk is a group, and H is a subset of G, such that H, asterisk is also a group, then H, asterisk is called a subgroup of G. So H, asterisk is called a subgroup of G. It's called a subgroup of G. So I want us to take the following remarks. That is, when I say remarks, what you should take cognizance of. Let's take the following remarks. There are 3 that I'm going to give us. The first one is that if we observe, the first one is that let's observe that G, that is the group, and A, which has only the identity elements as the element in A, are subgroup. They are subgroups, a subgroup of G called the trivial. They are called the trivial subgroup. They are called the trivial subgroup. Please, let's note that if you are asked to define a trivial subgroup, so they are called the trivial subgroup. This is what you are saying. Let me just give example. I can give example. If G, let's say G is an integer under addition. You know, an integer under addition is a group because all the four properties that you check for in the group, you can get it here. So, what are the trivial subgroup of this integer? Of course, natural numbers under addition can be a proper subgroup. It can be a trivial subgroup of this because there are two things that I check for. The set itself. You know, a set is a subset of itself. If a set has three elements, let's say a set A is equal to 1, 2, 3. A is a subset of A from our knowledge of set. So a set is a subset of itself. So we observe that G is a group G. And when we have A, which is just the element of the identity element, it consists only the identity element. These two are subsets of that group. An empty set, just like an empty set. An empty set is a subset of any set. So in case of a group now, when we come to the subgroup, the first thing that we should notice is that when we have G and A, which is just a set of an identity element, are subgroup of G. And in this case, they are called the trivial subgroup. So that's the first thing I want us to note under the remark. They are called the trivial subgroup. We also have some other subgroup. Then two, let's take note of this second point. Two, let's take note of this second point. Two, the identity element. The identity element of H is the same as that of G. What are we saying indirectly here? That is, if H is a subgroup of G, they have the same identity elements. That's what we are trying to say. That if H is a subgroup of G, they have the same identity element. Of course, we know the meaning of identity element. For instance, if you have a natural number under addition, the identity element here is otherwise known as the neutral element. So under addition, the identity element is 0. Under multiplication, the identity element is 1. So whatever you add to 0 will still retain its value. Whatever you multiply with 1 will retain its value. So what we are trying to say now is that the identity element of a subgroup and the group are the same. So please take note. That is the second property. By the time I give examples, so that we will be able to understand the concept. Then the last remark, the last point of that remark, every subgroup of an abelian group, every subgroup of an abelian group is abelian. Of course, abelian group is just a commutative group. If you can define a group, just add commutative property to that group, it becomes an abelian group. Abelian group, if you have to check if a particular set is an abelian group, just check for 5 properties. Check for closure, associativity, you check for existence of identity element, existence of inverse element, then commutativity. So if you are able to check for those 5, then it becomes an abelian group. Abelian is simply means a commutative. Abelian group is the same thing as commutative group. So those are the 3 properties that we should note. Now let's take examples. Example. You can be asked to give us an example of a subgroup. Each of integer under addition, rational number under addition, real number under addition, then complex number under addition is a subgroup. Is a subgroup of the next one. That is this what we are saying. You know, integer, they are the positive. Integer consists of positive, negative, and 0. Positive whole numbers, 0 and negative whole numbers. But it does not consist of fractional numbers that are fractional. Like, for instance, 3/2. So this is a subgroup of this. Integer is a subgroup of rational number. When I introduced set of numbers, I said natural number is a subset of integers, while integers is also a subset of rational number. No, natural number is a subset of integers. Integer is a subset of rational number, and rational number will be a subset of real numbers. While real number will also be a subset of a complex number. Complex number is the largest number under consideration because it has both real and imaginary parts. So please note the following. All right. At this point, I want to state a theorem, and this theorem is very important. I want to state a theorem. This theorem is very important when it comes to subgroup. Theorem. Let H be a subset. Let H be a subset of a group G. Then H is a subgroup. It's a subgroup of G if the first condition, if H is non-empty. Then the second condition, whenever we have an element AB that belongs to H, then we must have A, B inverse must belongs to H. So these are the two conditions that must be satisfied for us to be able to call H a subgroup of a group G. It's just two things. Of course, at the inception of this course, group theory, we have said that we are not concerned with non-empty sets. A non-empty set is a set that has no element. So once there is no element, there's nothing we want to do about it. The set under consideration must contain at least one element. So let G be a subset of a group G. So for H to be a subgroup, it must be a subset of a group G. Then H is a subgroup of G if the first condition, H is non-empty. It must be non-empty. And in this case now, it's just talking about existence of inverse element, which is the last point, the last property that we check for in a set. Because if AB belongs to H, then inverse of B must belong to H. So if these two conditions are satisfied, then you can generalize that H is a subgroup of G, and that is the summary of what we have been saying since morning. So let's take example. I want us to take an example now. Let's take example of subgroup. Example. Let me start with the first example. Example. Verify that the subset G, which is 1, 3, 7, 5 of Z8 under multiplication modulo 8 forms a group. So that's what we are given. That's what we want to do. Now let's look at it critically. Then that's the first part of the question. The second part now says find all the subgroup. Find all the subgroups of G. So this is 3-in-1 question. We first verify that the subset G, that subset G of Z8 under multiplication modulo 8 forms a group. So first test that this Z8, this subgroup, the subset is a subgroup, forms a group. Solution, what do? Let's first list out what we are given and what we are required to find. So we are given Z8. What are the elements of Z8? What are the elements of Z? That is integer Z8. It's going to start from, integer starts from, in this case now, since it's Z8, we are going to start from 0, 1, 2, 3, 4, 5, 6, 7. So these are the elements. It must be up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is Z8. If this is Z6, it will be from 0 to 5. But if we have Z 8 asterisk. This simply means that you exclude 0. It's exclusion. You exclude 0 from the set. Please note. So if there's asterisk there, you exclude 0. So this is the date. Okay. Then we are given G to be equal to 1357. This will be 57, not 75. 57. Okay. That is G. So we want to check, want to verify that this G forms a group. So how do we verify that? Of course, it's under multiplication, so we know what to do. So the multiplication table now, the multiplication table for G is, it's under multiplication. So I'm going to generate a table for G now. So let's see how we are going to do that. So G is just a subgroup. It's a subset of H. G is a subset of Z8. So this is how I'm going to form the table. The operating side, the binary operation is multiplication. The elements are 1, 3, 5, 7. 1, 3, 5, 7. So the question is, we have the question as G, which is G of Z8 under multiplication modulo 8. So if we are doing multiplication under modulo 8, everything that we get here that is more than 8, we are going to remove it from 8. This is what I'm saying. 1 times 1 is 1. 1 times 3, 3. 1 times 5, 5. 1 times 7, 7. So in that first row now, we don't have problem. Now let's see the second row. 3 times 1, 3. 3 times 3, 9. We are under modulo 8. So that will be 9 minus 8. That is 1. We write out the leftover. Then 3 times 5 is 15. 15 minus 8, 7. We write it here. Then 3 times 7, 21. How many times can 8 goes in 21? That's 2. That's 16. 16 minus 21, that's 5. We have 5 here. Please, let's look at it very well and get it. Look at it very well. If there's any question, you let me know. Look at it very well. Oh. Look at the table very well. When we come to this space, 5 times 1 is 5. It's less than 8. But 5 times 3 is 15. How many times will 15 divide 8? 8 divide 15, 1. Remainder 7. You write out the remainder. Then 5 times 5 is 25. How many times will 8 divide 25? That's 3. 24. Remainder 1. You put it there. Then 5 times 7 is 35. 8 in 35. 8 in 35 is 8 in 35 is 32. Remainder 3. Then we'll do the same thing there. 7 times 1 is 7. 7 times 3 is 21. That will be 5. That's 16 minus 5. 7 times 5, 35. 35 minus 32, 3. Then 7 times 7, 49. 8 divided by 49. 8 times 6 times 6, 48, remainder 1. That is the table that we are going to use. So that's the table that we are going to use to test for what we are looking for. So in this case now, the question says that we have to verify that the subset G, of course, G is a subset of Z modulo 8, and these are the elements of G. So modulo is multiplication. The operating sign is multiplication. That's why we generate. That's why we have to generate this table. We want to check that this forms a group. How do we do that? We start from the first property. We look at the closure property. Let's test for the closure property. The closure property. So you can call it closure law or whatever. I can call it closure property or closure law. Just when we have a groupoid, that's what we want to test for. What can you say about this table? You realize that all the elements that you have in G, 1, 3, 5, 7, if you check the row and column in this table, that is what we are going to get. That's what we are going to tell. Just the closure property is satisfied. Why is it satisfied? Closure property is satisfied since all the products are elements of G. That is, for all A, B that belongs to G, we can have A, B that belongs to G. That's what you have done. If you multiply, irrespective of the element you pick, and you multiply, at the end of the day, you still find the element there. So we are still going to find the element there. That's what we are trying to say. So the closure law or the closure property is satisfied. We go to the second one. That's associativity. Associative law. That is, if you pick 3 elements, irrespective of the arrangement, are we going to get the same thing? That's what we have. Associative law holds since, this law also holds since for all A, B, C that belongs to G, A, B multiplied by C will give us same thing as A multiplied by B, C. Let's check it out here. Let's pick 1, 3, 5. Let's pick 1, 3, 5. Let me just do it somewhere. So if I say 1 times 3 into brackets times 5, are we going to get the same thing as saying 1 multiplied by 3 times 5? Let's check. 1 times 3 is 3. This is 3. 3 times 5. 3 times 5. 7. So now let's check it out here. 1 multiplied by, what is 3 times 5 here? 3 multiplied by 5. That's 7. 7. Then what is 1 times 7? 1 times 7 is 7. So pick any element here. Take the first two. Relate it with the last, the third one. Or you take the last two. Relate it with the first one. You realize that you are still going to get the same answer. So since that holds, then we can conclude that associative law or associative property holds. So that's the second property to check under a group. Then the third one is the existence of identity element. And of course, under multiplication, the identity element, if you are very vast, is 1. The identity element is 1. That is, just say for all x that belongs to G, that any of the elements that belongs to G, 1 times x can be same thing as x times 1, and it's going to give us x. That is what we want to check. Okay? This is what I'm saying. Do we have the extent of identity element here? Look at this first column. 1 times 1 is 1. 3 times 1, 3. 5 times 1, 5. 7 times 1, 7. It shows that 1 is the identity element. So there's existence of identity element here. We are able to replicate what we have. Identity element simply means neutral element. What you use to operate with something and you retain its value. So under multiplication, the identity element is 1. So in this table now, we are able to we have seen that there is existence of identity elements. So we have checked for the 3 properties out of 4. So let's go ahead and check for existence of inverse elements. If we're able to get that, then we conclude. The fourth one, existence, which is the last one, existence of inverse. In this case, which is equal to 1. That is, what we're trying to say is that this V now is inverse of x. That is, x inverse or x inverse x must give us 1. Now let's check. Let's assume each of the elements here is x. So where do we have x inverse? That will give us 1. Let's check. For 1, what is the identity element? What is the inverse element of 1 there? Look at it very well. What is the inverse element? For 1, the inverse is v. The inverse element is v. For 1, this is it. For 1, v is equal to 1. Then for 3, v is equal to 3. Look at, how do you get your, indeed we have gotten our identity element to be 1. Our identity element is 1. So inverse element is something you relate. If x is an element, then the inverse of x, when you relate it under multiplication, we must get 1. So what will I multiply with this element x that gives 1? That's what I'm trying to check. Look at this. 1 times 1, I'm able to get 1. Where will I get 1 here? 3 times 3 is 1. Look at the third one here. 5 times 5 is 1. So these are the identity elements. So how do we get the identity? You say for 5, the inverse element is also 5. Then for 7 also, the inverse element V is also 7. So it is also 7. So every element of G is its own identity. So in this question now, every element of G is its own identity. Okay? And there's what we call that. When we get to that concept, I'm going to tell us. Every element of G is its own identity. So we can conclude that every element of G is its own identity. That's what you discover. Thus, G is a group. So we have been able to show that G is a group. So we go to the second part of the question, where we are asked to list out all the properties, all the subgroup. So where we are asked to list out all the subgroup. I want to adjust this a bit, okay, so that you'll be able to see it very well. So the subgroup, the second part of the question now, the subgroup, the subgroup of G are the first one. When we talk about trivial subgroup, I say under trivial subgroup, G will be the subgroup of G, and A, which is the identity. So when we have the group, the element that we are given, and the identity alone, we call the two the trivial subgroup. Every other subgroup are called the proper subgroup. So please let's note the subgroup of G are the first one, we can call it A, is where we have the identity alone, that's 1. Then B, I'm trying to break it down. 1, 3 can be subgroup. We have picked 1. 1, 3 can be subgroup. And that subgroup, let's say C is 1, 5. 1, 5 can also be a subgroup. Then another one is 1, 7 can be a subgroup. And G itself is also a subgroup. 1, 3, 5, 7. Why do we pick this as the subgroup? You know, under the theorem that we stated the other time, please check the theorem that we stated the other time. We are given that for let H be a subset of a group G, then H is a subgroup of G if H is non-empty. In this case, G is non-empty, and where we have for all AB that belongs to H, AB inverse must belong to H. That is, you realize that when we find the identity here, the identity element is 1, 1, 1, 1. So, and in this question now, G, every element in G is its own identity. So that's why we pick the first subgroup is 1. The second one is when we have the third element and 1. This is the identity. The third one, where we have picked the element and 1, this and 1, then this is the last one. So please, I want you to go over that theorem very well, so that you'll be able to understand what I've done here. Then out of this now, out of this subgroup, there are 5 subgroups here. We can classify this 5 into 2. There are 5 subgroups there. So we can classify them into 2. So the trivial subgroup here, we can break down to the trivial subgroup here. The trivial subgroup are A, which is the identity, and G itself. Then we also have proper subgroup. These are the 2 types of subgroups that we have. Proper subgroups. The proper subgroup that we have here now, the proper subgroup of G are B, C, and D. So these are the proper subgroup, B, C, and D. These are the proper subgroup. But when we have only one element, which is the identity, and that group itself, they are called the proper subgroup. So that is what we have here. Because of our time, I would love to stop here because of our time. So you can check standard textbook on abstract algebra, so that we can find more examples when we have groups and subgroups. So I'd love to stop here. Then we'll continue from there. So in our next class, we are going to talk about cosets. So we'll be talking about coset and index. How do we find a coset? Still under group O. So I'd love to stop here. Thank you, and God bless you.